Good morning and welcome to EMC Live 2017 Bootcamp. I'm Graham Kilshaw with Interference Technology. It is 10 a.m. on the East Coast of the United States here, and welcome to this year's Bootcamp. We have almost 1,800 registrations for this year's event. That's almost a record. And we have people watching and listening live from around the world, so welcome to all of you, the attendees. Today's keynote presentation is titled Managing Energy Flow in High-Speed Circuit Boards Using Field Theory. It'll last approximately 35 minutes, followed by a short 10-minute question and answer session, which will be moderated by our Senior Technical Editor, Mr. Ken Wyatt. You can ask questions at any point during the presentation. Simply use the Q&A button at the bottom of your screen, and we'll get through as many of them as possible at the end of the presentation. The presentation is available for download. You can simply use the document icon at the bottom of your screen. And before I present today's keynote speaker, I'd like to say a big thank you to our sponsor of this year's event, Rohde & Schwartz, without whom these events would not be possible. And so our presenter today is Mr. Ralph Morrison. Ralph is a graduate of Caltech and USC. He's been a leading pioneer in the field of high-frequency and high-reliability electronic control system design. His vast experience spans applications from aerospace to military, both as a primary designer and a hired gun when things went wrong. He's also the author of 14 books on electromagnetic fields, shielding, and grounding. And so, without further ado, over to you, Ralph.
Thank you very much. Before I begin my talk about interference in today's fast logic digital world, I want to thank Dan Beaker of NXP for all his support and encouragement. If it weren't for Dan, I doubt my new book, Fast Circuit Boards, would have been written. I want to thank Ken Wyatt for asking me to be the keynote speaker. I hope I can live up to his expectations. In the limited time I have, I want to give you some insight into how to view the world of fast logic. I believe that circuit theory is being stressed to its limits. We need circuit theory, but we also need to widen our view so we can avoid errors in circuit board layout. The ideas I will present have all been put into practice, and they all work. These methods do not involve computer programs or fancy measurements. They involve an understanding of how energy is moved in different conductor geometries. Many of the problems we have today result from not recognizing how nature behaves. She treats interference and signals the same way. To her, circuits provide an opportunity to store less potential energy. The distances can be miles or centimeters. It is our job to keep signals and interference separated. Our senses are limited. All we need to do is mention subjects like relativity, time warp caused by gravity, and quantum mechanics to make my point. We seek zones of understanding that connect with our senses. We have learned a lot about electricity, and we expect to continue along this path. There are many issues that are pulling electronics away from our comfort zones, and circuit theory is certainly a comfort zone. Fast rise times create a set of problems that circuit theory does not address. Transmission line theory has been a part of engineering since the early days of radio. The basics involve sine waves, matching impedances, and how to radiate energy efficiently. I want to discuss transmission lines that move logic signals between components. These transmission lines are shorter, the voltages are step functions, and the transmission lines are often traces spaced a short distance from a conducting plane. Early circuit boards used integrated circuits with long rise times. Circuit board technology improved to the point where all a designer had to do was interconnect all the components with traces, and the circuits would function. This world has changed. Rise and fall times in logic have shortened, and reflections and radiation can limit performance. We are at a point where transmission lines need to be designed. Trying to increase logic speeds and at the same time avoid radiation and crosstalk takes engineering. In this talk, I want to review basic ideas that will make it easy to design circuit boards and that will work the first time. Redoing a design is expensive. Let's see. I want to be on 7.
Okay, click. There you go.
The movement of information requires moving field energy on transmission lines. Problems occur if this energy is not immediately available. Circuit theory does not address the problems of moving energy. Nature will take any opportunity to reduce potential energy. This is why a rock falls, sound propagates, pendulums sway, and voltages move along a transmission line. Circuit theory is not intended to treat the transient problems presented by fast logic. It is a sine wave-oriented subject. It is voltage-oriented. Next slide.
Did it go?
There. No, one is one side. Next slide. Energy leaves, we move energy from storage to provide a logic signal to a gate, and then we need to dissipate this energy. The problem, we want this energy to occur quickly in various conductor geometries. In most cases, we need multi-layer boards interconnected by traces and vias. I want to discuss logic designs where picoseconds are becoming important. In the time I have, I can only outline some of the issues. I hope you'll benefit from the ideas that I present. To introduce you to electrical energy, we can start with the electron. It takes work to bring a group of electrons to a conducting surface. The work it takes to move a unit of charge in this force field is defined as voltage. Voltage differences can exist in space, even if we cannot measure them. On a practical basis, we can only measure potential differences between conductors. Electron motion is current that generates a magnetic field. Energy is stored in this magnetic field. Both of these fields can exist without electrons when energy is in motion in space. We're going to discuss energy that can be stored or moved in the spaces between conductors. A transmission line is such a conductor geometry that allows us to move energy on a circuit board. The fields that move this energy require current flow in the conductors. This current flow is the electron motion. The power industry uses power poles to support the conductors that move energy in the intervening space. On a circuit board, energy is stored and moved in fields mainly between the traces and conducting surfaces. To remove the emphasis placed on electron motion by circuit theory, here are some facts. I assume you and I are a few feet apart. If the fields from 1% of our electrons were free to push us apart, what would be the force, the size of this force? The answer is unbelievable. It is enough to lift the Earth out of orbit. This means that very, very few electrons are needed for any electrical circuit activity. The velocity of electrons in a typical trace is perhaps 2 centimeters per second. Wavefronts and energy travel at 300 meters per microsecond. That's a big difference. In a typical trace with 100 milliamps flowing, 1 trillion electrons are in motion. To us, 1 trillion of anything along a 10-centimeter trace is a continuum. The fact is, only 1 electron in 1 trillion is moving. To a moving electron, all its neighbors are stationary. The conclusion is electron motion does not explain the movement of energy. I just want to make that very, very clear. There is almost no energy stored or moved in conductors. So where is the energy? It is always in spaces, and it is not explained by electron motion. It is stored and moved in fields in capacitance and inductance. In free space, we have capacitance and inductance. Out in space without conductors, energy must be moving. It can't be stationary. When there are conductors, energy can be stored or moved in defined spaces. We have learned how to release this energy into space, and we call that radiation. We do not measure energy directly. We only measure volts and amperes on the conductors involved. In many ways, fields only define our senses, and it is a struggle to accept the view that this energy is not carried in conductors. The force fields are the magnetic or H field and the electric or E fields. A conductor geometry designed to store E fields is a capacitor. A geometry designed to store magnetic field energy is an inductance. Energy motion requires that both fields be involved. A transmission line can store both fields and is ideal for moving energy. On a circuit board, the fields are linked to the conductors, traces, vias, and conducting planes. In a decoupling capacitors, the fields are linked to the plates of the capacitor. E and H fields around a trace over a ground plane are important. This figure shows the E and H fields. See, we should be on 12. There we are. This figure shows the E and H pattern around a typical trace. This pattern is behind a wavefront. For logic and motion, the field pattern is unchanging and static except at the leading edge of a wave. For carrier power being sent to an antenna for radiation, the fields are in constant transition all along the transmission path. Step functions give us a different view of energy transmission. It's a view not seen when a carrier is involved. This slide is a presentation of the wave action that occurs after the switch.
This one?
Yeah, go ahead. No, it's the next one. Trouble's getting it.
There we go.
There we go. This slide is a representation of the wave action that occurs after a switch connects a voltage source to a transmission line. What is important to note is that the electric and magnetic fields are stationary behind the wave front. The wave front is converting flowing energy to electric field and storing it in the capacitance of the line. Is this 14? No, we need the next.
That one. There you go. Wave transmission?
No, we're not quite there.
Okay.
The wavefront is converting flowing energy to electric field energy and storing it in the capacitance of the line. The static field behind the wavefront are also carrying energy forward. When the wave reaches the matching resistor, all wave action stops, but energy keeps moving into the resistor. We know that as Ohm's law. 14. Yeah. The voltage in a transmission line that is long enough, there will be voltage doubling at the open circuit. This view graph shows the issue of voltage doubling. It can do damage to a component. On a practical basis, termination resistors are needed for clock rates above 1 gigahertz. A shunt matching termination resistor makes the transmission line look like it's infinite in length. The problem with this approach is there is a constant dissipation in the resistor as long as voltage level is present. We are reaching a point in our designs where this voltage doubling problem is an issue. It's important to realize for the unterminated line, the reflected wavefront deposits forward-moving energy into the electric field. This wavefront is moving in a direction opposite to energy flow. You cannot use the wave direction to determine which way the energy is flowing. The energy flow from the source continues until a reflected wave somehow returns to the source and changes the conditions. At this time, a new set of conditions will take place. This is not circuit theory in any sense. It's a key point. What we see when we have a wavefront is energy in transition, and without thinking it through, we don't know quite what that transition is. It can be energy is reflected, stored, or converted. The only source of new energy is a voltage source, and a decoupling capacitor functions as an energy source for step functions, and this force is just a few ohms for a short period of time. Here is a brief review of the present circuit board technology. Logic circuit boards are designed using laminates of copper and glass epoxy. Transmission lines are formed by etching and are depositing conductors on a dielectric. The return path for most transmission lines are what are called ground or power planes. I assume that most of you are familiar with this technology. That includes characteristic impedance, trace dimensions, the use of vias to connect transmission lines between layers, and the use of decoupling capacitors. Over the years, clock rates have risen, but characteristic impedance has stayed fairly constant at 50 ohms. 5 ohms is impractical, 500 ohms is greater than the impedance of free space, and the geometric mean is about 50 ohms. This value is not going to change. In a typical logic transition, a voltage source supplies energy to the transmission line. Behind the leading edge, there is voltage associated with the electric field and current flow associated with a magnetic or H field. The current flows out on the positive conductor and returns on the negative conductor. And this occurs at the leading edge. The electric field is in transition at the leading edge. The changing electric field in this region of space is called a displacement current. This is where the forward current crosses over and continues as return current. As the wave progresses, the loop area for current crosses. As the wave progresses, the loop area for the current increases. The current path outlines the space used by the flow of energy. The return current supports forward energy flow and has nothing to do with returning energy. The only place where a transmission line can radiate energy is at the leading edge. Behind the leading edge, there is no radiation, even though energy is in motion. An analogy that is sometimes helpful is to consider the energy path as a highway and the conductors as curbings. For a fast roadway, the curbing is continuous and the road width is constant. In electrical terms, the characteristic impedance must be constant. No cross traffic is allowed. The roadway cannot empty into a parking lot or suddenly narrow. It does turn out there can be a 90-degree bend and there will be no reflection. In a practical circuit, the closest we can get to an ideal voltage source is a decoupling capacitor. The point of demand for energy is usually inside an integrated circuit, and the capacitor is located at or near the pad connections on the circuit board. Assume the conductor making the connection from a transmission line has the characteristics of about 50 ohms. If the switch closes on a 50 ohm line, the voltage will drop to half. There's no way to avoid it. The impedance for sinusoids of the capacitor is another topic. To avoid having a transmission line in series with a decoupling capacitor, the capacitor must be a part of the integrated circuit package. Here are some first energy sources. What actually happens when a logic element makes a demand for energy involves these local sources. There are locally connected logic, the connections to a local decoupling capacitor, and the possible connection to a power plane. The distances involved vary, and the wave action is very complex. To further complicate the story, the return current path in the component is usually shared with many transmission lines. Stated simply, the characteristic impedance of the conducting path from the die to the mounting pads is not fully controlled. Remember, 50 ohm transmission lines take 5 mil spacings. Efforts have been made to use a closely spaced ground plane power plane as a decoupling capacitor. The problem with this approach is that the characteristic impedance of such a source falls off at 1 over R, and it starts out at about 50 ohms. Any attempt to raise the capacitance by using a high dielectric constant for insulation is self-defeating, as the velocity in a high dielectric is simply less. The velocity drops. A close spacing does not allow for practical trace runs. It is always less expensive and more effective to use standard decoupling capacitors for local energy. In fast circuits, most of the problems revolve around reflections and transmissions. If there are a large number of reflections and transmissions, we have more radiation and we have time delay. The next 2 slides show the equations that describe this activity of reflection and transmission. I don't expect you to get all the details at this point. Only important to realize that this is a key issue. With the IC package, there can be reflections, and this adds to the delays that limit performance. Understanding these equations is basic to understanding issues involving all high-speed logic. What becomes very clear is that reflections should be avoided as they add delay. That is what I meant by a smooth highway. We don't want any changes in the characteristic impedance. Otherwise, we will have delays. The reflection coefficient works for sine waves as well as step waves. At a short or voltage source, the coefficient rho is -1 if the reflected wave cancels the arriving wave. At a matching impedance, rho is 0 and there is no reflection. At an open circuit, rho equals 1 and the reflection voltage is equal to the voltage source. The return voltage is double the arriving voltage. For transmission, the coefficient works for sine waves and step functions. At a short, tau is 0, at an open, tau is 2, and the arriving voltage is doubled. At a match, tau is 1, and the wave is not reflected. There are several ways to show wave action. In the next few slides, I have made a new way to show reflections and transmissions. In most practical cases, the number of separate waves can reach 100, and this is not easily displayed. The wave amplitudes and polarities are not shown in this display. Amplitudes are indicated by the value of W. There can be one or two waves at each transition point. The initial wave is concluded. The energy that is flowing or in transition behind the wavefronts then takes on one or two new paths. This slide shows arriving energy at R is W1 plus W4. This is, let's take the next one. Here's an example of that picture. The final arriving voltage is the sum of those two waves. So we start out with a wave going forward and backwards. It reaches the transition at the resistor and enters the resistor in two steps. This is an optimum method. The initial wave moves forward as one half the voltage. Pardon me, let's take the next view. There. Now, this is an optimum method. The initial wave moves forward as 1/2 V. Half the voltage goes forward. At the termination, the voltage doubles to V. The reflection returns V to the source. At the source, all wave activity ends, and the entire line is at voltage V. No current flows. The switch grounds the resistor to return the line to 0 volts. There is no resonant action. See what the next one is. This display shows the complexity of wave action when a logic switch closes on an integrated circuit and the transmission path involves external energy source V, a 50 ohm transmission path, and two 100 ohm paths inside of ICs. Within a short period of time, there are 100 waves. This is the reason why I make this type of presentation. All of this wave action limits the maximum clock rate that can be used. It is not the circuit in the die itself, but it's the structure of the interconnections that make the big difference. This is not one logic transition. Wave action is delay and radiation. Most of the problem could be avoided by matching impedances. Resolution of this problem requires action by both the user and the manufacturer. Here's a situation that shows you a problem that involves multi-layer boards. I want to show you that we have a transition from strip line to microstrip. Circuit boards with multi-layers are a problem because we divide the field into two parts and then try to bring it back together. What is very, very important is that there be a via connection at the right place so the field has a good chance to combine. If this via is not control, if the connection to the strip line does not have a ground to ground connection near the transition of the via, we're going to have fields spread out in the region between the two conducting planes, and there will be board edge radiation. The transition path is generally a controlled cylindrical space. This means that there must be gaps in the ground planes at vias to allow for this cylindrical path to take place. If the return path puts a bump in the road, the spreading field can leave the transmission path and radiate at the board edge. Reflections can occur that delay getting the initial wave to its destination. There's a big problem when it comes to power planes and ground planes used at the same time. In general, I don't recommend them. Fields that share the storage space can easily cross-couple into logic fields, and this is interference. If the power space is used for strip line, then decoupling capacitors are required at the transition to provide a path for return current for each signal. If you examine this slide carefully, you can see that the path for current is convoluted. It is not very easy to make a transition that is smooth. The roadway is, in effect, blocked. This is not high-speed logic. It's the wave action that converts energy and back and forth to electric and magnetic field, and this is complicated. Next. What I would like to tell you next is that the reflections that we get at double voltage are really the first part of a wave action that is really called a resonance. The resonance phenomena is the back and forth motion of a wave between a voltage source and an open circuit, for example. So the first return wave is converting part of the incoming energy to more electric field energy. And if you examine the details of this view graph, you can see that this is happening. What generally is happening is we don't want this resonant phenomena to take place. That's the reason why we must have these terminations. Of course, if the rise time is long enough, there is no problem. We are getting into the region where this energy flow issue and resonance can be a big issue. Now, the next slide shows the next two portions of the wave. What is important here is that the return wave now is converting electric field energy to magnetic field energy. By the time we get the full round trip twice, we have converted electrical field energy to magnetic field energy and back to electric field energy. These transitions are not the movement of energy, they are the transition of energy. So we have to be careful of how we view wave action. I have just a final thought that I want to present to you. I've given this little phrase quite a bit of use, and maybe some of you have seen it. Buildings have walls and halls. People walk in the halls. Circuits have traces and spaces. Energy travels in the spaces, not the traces. We have to change our viewpoint. We have to be willing to accept the idea that we need to design the spaces, the roadway, not the curbings, in order to get energy to flow correctly between points. We want to avoid reflections if at all possible, because they are delays, they are radiation, they are problems. Here are some facts that you will probably recognize. We have reached a point in circuit layout where clock rates have peaked and radiation is not controlled. To avoid problems, a change in approach is needed. It starts with understanding how nature behaves. Take away circuit ideas and refuse to accept moving energy makes it a big guessing game. Another problem is inertia, ego, turf protection, conflicting messages from experts, and this all adds to the challenge. The bridge to a new approach may seem difficult, but in the end, it's like driving on the other side of the road. It is easy to do with practice, and then it becomes automatic. This is the key idea. All electrical activity is nature spreading out energy. This is all there is. It is predictable. It is repeatable. It's the whole story. It is this understanding that is needed to take the next step in design. It is fundamental. I also know this way of thinking is different. It is a new playing field. It takes time to learn to work with these new ideas. This ends my talk, and I want to thank you.
Thanks so much, Ralph. Excellent presentation. We do have some time for questions, and I see they're starting to appear here. Let's just start off with one question. do ground planes shield against radiation? That's a pretty common question among my clients, at least.
Trying to locate the question.
Sorry, Ken, what was the question?
The question is, do ground planes shield against radiation?
Okay, go ahead.
Ground planes, in general, are intended to be the return path for current and transmission lines. Radiation is confined or bounded by the presence of the ground plane, but it doesn't, in a sense of a box, shield the fields. The fields are, when they're constrained between a trace and a ground plane, just do not leave, or very, very little of it leaves. And that's just because of the geometry. But to say that a ground plane in general is a shield, I think is not the correct way to understand what its function is. And in general, I wouldn't add ground planes to do shielding without understanding a lot more of the problem.
Right. And in my own seminars, I try and make the point that really when somebody refers to a ground plane, it's really a current return plane, and or signal return or power return, and not really a shield. Here's a question from the audience that just came in. It has to do with asymmetric strip lines. In other words, the strip line has more space on one side than the other. So here's the question. In asymmetric strip line configuration, if the spacings between the two planes from the signal layer is a 3-to-1 ratio, can we assume almost all the energy flows between the signal layer and the closer plane?
There very definitely is a difference in the energy level if it's unsymmetric, because the lower impedance side, if you define the voltage, implies that that side is carrying more of the energy, and it's unsymmetric. Yes.
Right. It makes sense. Yeah.
It makes in my way of thinking, it makes it more difficult to pull those two fields back together to provide the actual signal at the receiving point for that particular wave action. And when you're dealing with slow rise times, it probably doesn't make any difference. But I have a feeling that it gets to be quite a different story as you stretch the issues into higher and higher clock rates, because then it becomes more important to treat the side which is carrying more of the energy. I mean, that makes a lot of sense. But that is not a simple problem, because in the recombination, those are nasty problems. So I wouldn't know how to picture them very easily.
One question that comes up repeatedly has to do with gaps permitted in ground planes or ground return planes. And do you have any comments on that? The question would be, are gaps permitted in ground planes?
Well, gaps are needed when you have fields that must cross the ground plane, and that's a situation. Anytime you send a signal through a via that crosses a ground plane, there needs to be a gap for the return current for the field, and the return current must be involved, because the field and the return current and the forward current, the current path defines where the field is going to be. And if that path is circuitous, you've lost the field, and it will go off and do other things and radiate. So the problem has to be looked at from a field standpoint. It's not so much the gap itself, because there are gaps required. An isolated gap in the middle of a ground plane has no effect at all. Some gaps are needed in order to move the field correctly between points. The gaps that really have to be worried about are those where a trace crosses a gap and the field pattern is now affected, which means you have a reflection point. That's the gap that really is the big problem. And so if you examine these paths and look at the transmission path as a cylindrical place in space for the field to move, you won't have a problem. If there are no fields there, who cares? You can put the gap anywhere you want. In fact, in my book, I show that you can build working structures without ground planes, which means there's a gap everywhere. It's just that you must know how you are controlling the fields. If you control the fields, there's no problem.
Now, you mentioned your book. I understand you just finished your 15th book now, and it has to do with moving energy, or how energy moves in circuit boards. And do you address all these questions in your book, and when is that book coming out?
When's your book coming out?
Oh, that should be the first few months in 2018. And in fact, the copy edited version is finished, the book cover is finished, and it's just a matter of taking that last little few steps and then doing the publication. It should be out.
What's the name of it?
It is called, Fast Circuit Boards and Energy Management. Fast Digital Circuit Boards.
And so you'll be covering all these points in that new book, right?
Those points are covered in your book.
Well, yes. In fact, I was going to apologize. In just a 30-minute period, it's very difficult to take the content of an entire book and present it in a useful manner. So all I could do is provide highlights and hopefully connect them together in a way that could be understood. But it takes many, many more paragraphs to explain all the details. And I spent a great deal of time working on this book, and I think it covers this area with great care. And I think this is an important, very important step for the future. We just have to consider circuit boards as being devices for moving the electromagnetic field energy around. And not only moving the energy, but converting it. Because the mistake that's frequently made is that we think of waves as being just energy-carrying devices. That's not true. They carry, convert, and store. They do all things, and that's a much different view. And not only that, when you have reflections, you are starting a resonant process. And when there are 2 or 3 or 4 reflections, there are literally reflection points. There are literally hundreds of reflections. Those reflections are delays. You can have all the speed in the world inside the integrated circuit, but you can't realize it until you get rid of the reflections on the external structure.
Okay, excellent. Here's another question from the audience, and it has to do with the location of bypass capacitors or decoupling capacitors versus the spacing between ground and power planes. So the question is, how important is the location of the decoupling capacitor if the ground and power planes are spaced very close, for example, 2 to 4 mils apart? I think you may have addressed that in your presentation, but you might want to clarify that. Basically, they're asking is it really that important to locate the decoupling capacitor close to the IC if the ground and power are spaced very close together?
Well, I cover this in my book, but it just roughly speaking, the problem is you get capacitance between the ground and power plane. There's no argument there. However, the capacitance doesn't become significant until you move out a fair distance from the point of where you take the energy. In fact, it's very difficult to pull the energy from any source which is less than 50 ohms, which means that in the first centimeter or so, you're maybe down to 10 ohms, and then in the next centimeter down to a fraction of that. But it takes time to move out into the space to get the energy and bring it back. That's only a piece of the problem, because when you put a very high dielectric constant into position to get the capacitance, you slow the wave energy down, because the velocity of energy in a capacitance drops as the square root of the dielectric constant. So you lose. And not only that, the very close spacings make it very difficult to have the control characteristic impedance for the strip line. My conclusion is that it's not a very good device. In fact, it's cheaper and more effective to use decoupling capacitors. And although the idea sounded pretty good at the beginning, it didn't end up being a very good idea when the speeds get up to where they are. My feeling is that ground planes and power planes are useful, but power planes don't have quite the same impact that ground planes do. I think power planes have to be used very carefully. One of the troubles is the power plane, you're pulling energy from it, therefore there's wave action. And as I pointed out, some of the times this wave action gets significant. If you use the same space for a strip line, you're cross-coupling, and that is a noisy system. You may not see it in slower logic, but you will sure see it when things get fast.
Okay, excellent, excellent answer. So I think the main point is, so many people who have, we've all learned circuit theory, and so the important point or takeaway, I think, from your presentation is that it's not the flow of electrons that's carrying the wave. It's the space between the dielectric that the wave travels through, and so we really need to be careful of the geometry, I think.
That's true. The other thing is to avoid that causing that wave energy to leak out beyond the transmission line and all throughout your board. Do you have any last comments? The thing I see as a big problem is that the feeling that waves and energy are connected. It turns out that energy flow does not have wave action associated with it. It may be that there's energy flowing behind a wavefront, but the wavefront does not imply energy flow. Energy flows, you can't see it because the electric and magnetic field are stationary. And there's no radiation from stationary fields, but there is energy flow. That is an idea that really has to be carefully considered. That is usually not understood by people.
Okay, just one follow-up question, then we'll have to end the presentation. So if you use closer power, if the power and return planes are closer together, say 2 to 4 mils, doesn't that reduce the inductance or the spreading inductance to the capacitive properties of those planes.
Didn't quite. When you put
in other words, okay, let me rephrase that. Is the location of a decoupling capacitor unimportant through decreasing the spreading inductance of the capacitor by bringing the power and ground planes close together? Or is that just another question as far as pulling energy out of the power and ground planes?
Well, in order to take energy out of anything, it takes reflections. And as I pointed out, the characteristic impedance near the point of connection is still going to be about 50 ohms. You have to realize that the shortest possible connection to an energy source is a zero-length transmission line to a decoupling capacitor. That's the best you can do, because immediately at the entrance point to the capacitance, it looks like a few ohms in transmission line in characteristic impedance. It's not possible to do that with a ground and power plane, because it spreads the energy out into a significant area, and it takes time and reflections to move that energy out. Anytime you have reflecting processes, and in case of a ground plane, power plane, the reflection processes are in continuous transition. That's the only difference between that and a transmission line. In a transmission line, it's 50 ohms anywhere you look. If you could get it to be 5 ohms, that would be fine. But in a ground power plane situation, the lower impedances are quite a distance away from the point of entry, and that slows things down and means there's a lot of reflecting processes necessary to get the energy out, and that is time delay. That is what you can't afford. The ideal voltage sources, the ones we really want, are the ones that get the energy now, right now, not later. And that's the reason why you have to be very, very careful to make sure there is no transmission line in series with a decoupling capacitor. They should be right at the point of demand. And ideally, they should be inside the integrated circuit. When it really counts, you just cannot have any distance between the energy source and the point where it's needed.
Okay. Well, we need to wrap up. That's really all the time we have today.
Okay.
All questions submitted during this presentation will be answered on the website, and we want to thank Ralph for a very informative presentation. You all will receive an email with a link to the on-demand version of this presentation within about 24 hours. I'm Kenneth Wyatt, Senior Technical Editor for Interference Technology. Thank you for attending EMC Live 2017 Bootcamp.